morning, dear students. Today we shall see the one-dimensional beams. We know that beam is a structural member which supports transverse loads. Beam is a long member. Beam is a slender member which supports transverse loads. Examples for the beams are long horizontal members used in buildings, bridges, shafts supported in bearings, right? These are the examples for the beam. These are the examples for the beams. Long horizontal members used in buildings, bridges, and shafts supported in bearings are the examples for beams. In this particular chapter, we discuss beams with symmetrical cross sections. Beams with symmetrical cross sections with respect to plane of loading. With respect to plane of loading. Right? Now, we have a one-dimensional beam here. Okay. One end is hinged, other end is supported on rollers. We have a beam of uniform cross section. We have a beam of uniform cross section. Now, this beam supports distributed load, concentrated load, and coupled. Right? P is the load intensity. It is the load distributed per unit length. Right? And PM is the point load acting at point M. MK is the couple applied about an axis through point K. Okay. And L is the length of the beam. Now, when you apply these loads, beam bends in the form of arc of the circle. In the form of arc of the circle. Here, the distributed load P is applied upward and concentrated force is also applied upward. And here the moment M applied at K, right, is acting in counterclockwise direction. Therefore, I assume that the beam bends in the form of arc of the circle like this, as shown in this diagram. As shown in this diagram. When you observe the beam section under the action of the transverse loads, it displaces from its original position, and moreover, the same beam section also rotates. The beam section displaces in the transverse direction, and in addition to the displacement, the beam section also rotates. Therefore, we determine the beam deflection and slope at any point on the elastic line. Okay. This is the deflected shape of the elastic line. Deflected shape. Deflected shape. Okay? Now, you can say deflected shape of neutral axis. This is the deflected shape of the beam. Right? This is a undeformed shape of the neutral axis. Okay? Now, if you take a section distant x from first end, if you take a section distant x from the first end, right? This section displaces by an amount V, right? And the same section also rotates counterclockwise by an amount, right? Say theta. So therefore, slope of the section, slope of the beam section, distant x from the first end, in addition to the deflection, you can determine. What is the deflection here? V, beam deflection. And what is the slope? It is V dash. If V is the beam deflection, V dash is the slope. The first derivative of the beam deflection, that is dV by dx, gives us the beam slope, right, at the same section. Therefore, for every section, for every beam section, you can determine the displacement and also slope. Understand? So, slope, slope of the beam is represented, by the slope of a tangent drawn to the deflected shape of the beam at the same point. Slope of the beam, V dash, is also represented by slope of a tangent drawn to the elastic line at the same point. Is also represented by the slope of the tangent drawn to the elastic line at the same point. That is V dash. Okay, now see here, we have two diagrams here. This is the beam section, and this diagram, tells us the variation of the normal stress with respect to beam section. As I said, we consider here a beam section symmetrical about the plane of loading. This is the plane of loading. This is the plane of loading, right? This is y-axis. Okay, this y-axis, if you observe, this section is symmetrical about this y-axis. As I said, we consider here in this particular chapter, the beams with symmetrical sections. This is a section symmetrical about y-axis. Okay. Now, neutral axis is passing through the centroid of the section like this. Neutral axis is passing through the centroidal. This neutral axis is passing through the centroid of the section like this. Okay. Now this is z-axis. Okay. Now, here the expression for the normal stress sigma, the expression for the bending stress sigma, which equals to m y by I. This is the expression for sigma. What is m? M is the bending moment acting on the section. I is the moment of inertia of this section. Moment of inertia of this section about the axis z. About the axis z. And what y represents? Y represents the distance of element from the neutral axis. The distance of the element from the neutral axis. Okay. On the same section, if you plot the variation of normal stress sigma with respect to distance of the element, right? How you get, you get the linear variation as we see here. Okay, sigma varies proportionately with respect to y, because bending moment acting on the section is same and moment of inertia is also constant. Therefore, you get a straight line. Okay. Now, according to this expression, the normal stress is maximum at the outer fiber. It is maximum at the outer fiber. Okay. Now, if the beam bends like this, with convex side upwards, tensile stresses are induced in the top fibers and compressive stresses are induced in the bottom fibers. Right? If the beam bends like this with concave side upwards, compressive stresses are induced in the top fibers and tensile stresses are induced in the bottom fibers. Okay. Now if you visualize our diagram here, the beam bends with convex shape upwards. The beam bends with convex shape upwards. The reason is the forces applied are acting vertically upward. Therefore, the beam bends like this, convex shape upwards. In this case, tensile stresses are induced in the upper fibers and the compressive stresses are induced in the bottom fibers. Clear? Now, okay. I hope you can understand these diagrams. Now, what is this? This is an infinitesimal element of area dA. Okay. This is an infinitesimal element of area dA. I assume that this section is considered on the beam distant x units from the first end. Therefore, the thickness of the section is dx. Understand carefully. Okay. I consider that this section is distant x units from the first support. Let dx be the thickness of the element, right? And the same section contains an infinitesimal element of area dA. Right? This element is distant y units from the neutral axis. Okay. Now if you go back and collect, the relations sigma equal to my by I and epsilon equal to sigma by E and d square v by dx square equal to m by EA. Right? Sigma is the normal stress or the flexural stress, we know it. Now m is the bending moment acting on the section, right? And I is the moment of inertia, y is the distance of element from the neutral axis. Okay. So here you can use minus for the compressive stress and plus for the tensile stress. Okay. So therefore you can write sigma equal to m by I, doesn't matter. You can write sigma equal to m by I into y. And the sign conventions plus and minus. We use plus for the tensile stress and minus for the compressive stress. Okay. Next, from Hooke's law, we know that epsilon equals to sigma by E because stress by strain equals to Young's modulus. E is the Young's modulus of the material. We consider here only the beams that are made of isotropic materials. We consider here the beams that are made of isotropic materials and also assume that the material is homogeneous. Okay. Now, from the elementary beam theory, we can also obtain this relation d square v by dx square equals to m by EI, where v is the beam deflection. V is the beam deflection. D square v by dx square equals to m by EI. Okay, where EI represents the flexural rigidity. As we know, m is the moment acting on the beam section distant x from one end. Okay, in our case we have taken this section distant x from the first end. Understand, these are the equations we can recollect back from the knowledge of the strength of materials. Okay, now as I said here the symbol sigma represents normal stress, epsilon denotes normal strain, m is the bending moment acting on the section, v is the beam deflection and I is the moment of inertia above z axis. Now, we know that the finite element formulation is done for all the one-dimensional problems, right? Using the potential energy approach. We can express the potential energy of the beam, right? We can express the potential energy of the beam as the sum of the strain energy of the beam and work potential. Work potential is due to the work done by the external forces. Now, we shall see the strain energy of an element of length dx. Firstly, we determine the strain energy in an element of length dx. Right? Now, I represent du as the strain energy in an element of length dx. In an element of length dx. I represent du as the strain energy in an element of length du. du equals to 1 by 2 into integral over area of the infinitesimal element sigma E into dA dx. We know how we get this, because what is the expression? The strain energy of an elastic solid U equals to the strain energy of an elastic solid U equals to integral of half into sigma into epsilon into d. This is the expression. Understand? Right? Because here we are considering a beam, a one-dimensional beam. What stress is induced across the beam section? Normal stress. It is the flexural stress. You can say bending stress. Therefore, sigma is the bending stress or flexural stress. Okay? Into epsilon, it is the normal strain. Okay? Now, dV, how you calculate this? That is the question. If you go back and see, we considered here an element, an infinitesimal element of area dA on the section distant x units from the first support. Distant x units from the first support. Right? Therefore, what is the thickness of the element? Dx into, now, what is the area of the infinitesimal element? dA. Therefore, you get dV equals to dx into dA. That is what we write here in this particular expression. That is what we write here in this particular expression. In place of dV, I write dA into dx. Understand? Now, this is the expression for the strain energy in an element of thickness dx, right, and area dA. Now, this equals to here 1 by 2 into, now we know that stress by strain equals to Young's modulus. We know that stress by strain equals to Young's modulus. Stress by strain equals to Young's modulus. This is one equation. Okay? And we also know that, M by I equals to sigma by phi. Okay, now, here, what we do is, we write in place of sigma, right? What we write? Sigma equals to My by I. This I put here. This I put here. So therefore, what I get in place of sigma, if I write My by I get My by I into epsilon, which equals to E. Now what is epsilon here? Epsilon equals to, I write My by E I. My by E I. Okay. Now I can replace this epsilon by my by ei. Now what I want? I want sigma. Now sigma equals to E into epsilon. Therefore, in place of sigma you write E into epsilon into, now in place of epsilon my by ei you write like this. Okay. Now what you get here? What you get here? E get cancelled with each other, right? And you get m epsilon y by I. Okay. Now what is epsilon? My by I is equals to my by I into, again, my by ei. Then what you get? M square. You get, how you get? You get like this. M square y square by E I square. Okay. Now m square by ei square I have here. M square by ei square I have here. It comes out into integral over the area of infinitesimal element into, right? Now y square we have y square into dA, right? So here you have to integrate this y square with respect to the area of the cross section. Okay. So therefore integral over the area of the section y square dA into dx. I hope now you understand how this is obtained. Okay. Now what is integral of y square dA? It is the moment of inertia I. That is what I write here. Integral y square dA over the area of the section. It is moment of inertia. Now du equals to 1 by 2 into m square by, see here, m square by ei square into I. Then you get m square by ei into dx. Because we replace integral of y square dA by I. Then you get 1 by 2 into m square by ei into dx. This is the expression for the strain energy stored in an element of thickness dx. Okay. Now, if you want the strain energy in an element, if you want the strain energy, in the elastic solid of length L, then you have to integrate this over the length of the solid. What is the solid here? Beam. L is the length of the beam. Therefore, now U equals to 1 by 2 integral over the length of the beam ei into d square v by dx square whole square into dx. Okay. How you get this? That is the question. We know that d square v by, we write here. We know that d square v by dx square equals to m by ei. M by ei. Okay. We have here m square by ei. M square by ei. Now what I do is I multiply this by ei and then I divide. Then what I get? Ei into m by ei whole square. What is m by ei? D square v by dx square. Therefore, m by ei whole square is d square v by dx square whole square. Hence, ei into d square v by dx square whole square into, you get as it is dx. Remember, this is the expression for determining the strain energy in the entire beam. Okay, this is the expression for determining the strain energy in an element. This is the expression for the strain energy in an entire beam of length L. Okay, you remember this. In the next class, we can derive the global stiffness matrix from the strain energy stored in a beam of length L. Understand? Thank you. Thank you very much.